Okay, photons and electrons. Where does the photon come from, or who thought of it as a photon? How can we know that it's a photon? Photons are super small, so how do we detect them? We had some ideas about charge and mass with an electron, but how do we figure this out? In this last video, we had some equations up there, and I realized we needed to back up a little bit. We need to talk about what's called black body radiation. Black body? Well, why isn't it white body radiation? Well, the problem is if you do a relationship between temperature and radiation, you don't want reflection off of that. And if you're looking at something white, most of the light reflects off of it. If you're looking at something red, just the red light reflects off of it. If it's black, then no light is reflected from it. So what we want is a black body representation. Now, how are we going to do this? Here's the experiment setup. We're going to take a black, I shouldn't say black, we'll just take a big square oven, big box, that's a better way to say it, a box oven that we can increase temperature in. And we're going to have a little hole in that box, which is going to be where we look at the radiation. That radiation is going to be in different intervals. In other words, what we want to do is find out which frequencies are more intense, which frequencies are less intense, so that we can draw a nice graph of this stuff. So here's what's going on. Inside that box, there are radiations that are like waves. And you might say, well, if it's black body, then you can't see the radiation. Well, if it's real low temperature radiation, not that hot, then you can't see it. All that's there is the infrared, the stuff that's lower frequency than what you can see. And if you think about an element on an electric stove, it's kind of grayish black, and it's kind of a good representation of something like this. Then as you heat it up, what happens? It starts glowing just faintly red. So now as you heat the temperature up, some of the frequencies are in a range that you can see them. If you could keep heating that temperature of that element up, first it would glow really bright red, and then eventually it would get, well, the element's probably going to burn out at this point, but if you keep cranking up the voltage so that the temperature of that element gets higher and higher and higher, it would eventually go up into kind of a yellowish, whitish look to it, which that's, look at the sun, that's a black body that radiates. If you shut off all the radiation or brought the temperature down to zero, it'd just be like a black ball. So as it starts heating up, you have these infrared and all these different rays of frequencies that go on. So back to this box. This box has these waves that are going to reflect off the box edges. And as they reflect off, some of those frequencies are going to be selected because of the dimensions of the box. There's the waves have a certain wavelength, and that wavelength becomes less as you increase the frequencies, but still only certain frequencies are going to be emphasized in this box. And at the little hole on the output of that oven, we can see the different frequencies that are coming off by using what's called a diffraction grating, which will cause different frequencies to bounce off at different angles, and then we can use a sighting mechanism and a detector to figure out what the brilliance is of each of those frequencies. Remember, what we're trying to do is find the relationship between temperature and radiated frequencies. And this was what Planck was trying to do. And what happened was he ran into a problem that didn't work, and I talked about that on the last video. So now we're going to focus on the math that's in this box. And next, I'll start drawing some figures and drawing some equations or writing some numbers down, and hopefully it's in a way that's understandable.